In this video, I'm going to be demonstrating the one sample T procedures. We'll be doing a hypothesis test and a confidence interval. To do that, we're going to be using this example with M&M bags. We want to know, is the weight of peanut M&M bags on average different from the weight stamped on the bag? To answer this question, 26 bags of peanut M&Ms were purchased from a local grocery store. Bags were selected from boxes at several different checkout lanes to get a representative sample. The weight stamped on each bag was 49.3 grams. Thus, our hypotheses were null hypothesis mu equals 49.3 and alternative hypothesis mu not equal to 49.3, where mu was equal to the mean weight for peanut M&M bags in the population of all peanut M&M bags. So first thing we do before we can actually do any hypothesis tests or confidence intervals is check the requirements. So there's two requirements for using the one sample T procedures. The first requirement is that the data comes from a simple random sample or equivalent, and the second requirement is that the distribution of sample means is normal. So for our first requirement, the simple random sample, I didn't exactly do a perfect simple random sample from the grocery store, but I feel like my sample is going to be representative of at least all of the M&M bags at the grocery store that I was at. So I did select from several different parts of the store so they didn't all come from the same box. So for the purposes of our study today, we're going to assume that we have a simple random sample or equivalent. The second requirement is that the distribution of sample means is normal. There's two ways to meet this requirement. First, if the population is normal, then the distribution of sample means will also be normal. The second, if the population is not normal, but the sample size is large, say 30 or more, then the distribution of sample means will be normal. So if either of those is met, then this requirement is met. So we don't have the population, obviously, but we can look at the sample, and if the sample is normally distributed or fairly symmetric, bell-shape-ish, then we can feel pretty good about the population being normal as well. So to do that, I went ahead and did a QQ plot within SPSS. So I went to Analyze, Descriptive Statistics, chose QQ plots. I put my variable over there, the M&M weights, and ta-da, this is what I got for my normal plot. And in a normal plot, the data is plotted in such a way on this special graph paper essentially so that if the data is normally distributed, then it will fall nicely on a straight line. And you can see that for the most part the data falls pretty close to that straight line. There's not like some giant curvature there or anything. In addition, I also did a histogram to look at that shape, and you can see that it does seem to have a relatively symmetric bell-shape-ish distribution. Also, my sample size was 26, not quite 30, but it's getting close there. So because my sample is roughly normally distributed, then my distribution of sample means can also be considered normal. So I've met the requirements. So now on to my hypothesis test. So remember, my hypotheses were null hypothesis mu equals 49.3 and alternative mu not equal to 49.3. In SPSS, we go to the Analyze menu, choose Compare Means, and then choose the One Sample T-Test. Once in there, I'm going to take those M&M weights and I'm going to pop those over to my test variables. Next, and this is really important and where a lot of students get messed up, is the default test value in SPSS is 0. Now the test value is the value that you're assuming under the null hypothesis. It's very, very important that you change this so that you get the correct answer. So under our null hypothesis, we said that mu was equal to 49.3, so I went ahead and changed that within SPSS. Then I go ahead and click on OK, and here's what I get for my results. So you can see I get my test statistic, T equals 7.845. That has 25 degrees of freedom, and I get a two-tailed p-value of 0.000. So one thing to note is that SPSS always is going to give you two-tailed p-values. So you have to look back at your hypotheses and figure out if you actually have a two-tailed test. So in our case, we had null hypothesis mu equals 49.3 and alternative hypothesis mu not equal to 49.3. Because I had the not equals to, that indicated the two-tailed test, meaning that this p-value is the correct p-value for my test. So in general, how to tell if you have a one-tailed or a two-tailed test, you look at the alternative hypothesis, HA. If there's a not equals to in the alternative, then it's a two-tailed test, and you can just use the p-value that's given to you by SPSS. If your alternative has either greater than or less than in it, then it's a one-tailed test. So you would take the value that you get in SPSS and divide that by 2 to get the real p-value, the one-tailed p-value that you want for your particular test. All right, so now we have our hypotheses, we have our p-value. It's time to start drawing conclusions. So what we're going to do, and this goes across the board for any hypothesis test that you're doing, is that you compare your p-value to alpha. And a typical value for alpha is 0.05. If p is low, meaning the p-value is less than alpha, then HO must go. So we're going to reject the null hypothesis. If p is high, meaning the p-value is greater than alpha, then we keep the guy, meaning we fail to reject the null hypothesis. When we're writing our conclusion about hypothesis tests, the conclusion has two parts. First, we're either going to reject or fail to reject the null hypothesis. So something to note is that we never, ever, ever say that we accept the null hypothesis. And we never say that the null hypothesis is true, ever. No matter what our p-value is, no matter what our data is, we don't say that the null hypothesis is true. The second part of our conclusion is all dealing with the alternative hypothesis, because the alternative hypothesis is really why we were doing this test in the first place. So if in the first part we reject the null hypothesis, that means that we have sufficient evidence that the alternative hypothesis is true. And in the first part, if we fail to reject the null hypothesis, that means that we have insufficient evidence for the alternative hypothesis. Now, of course, when you're writing your real conclusion, you're not going to use HA, you're going to put what the alternative is in there in words. But if you remember, reject H naught means sufficient evidence for HA, and failing to reject H naught means insufficient evidence for HA, then that can help you determine what the correct conclusion is going to be. So in our case, we had a very low p-value, definitely much lower than 0.05, an alpha level. When p is low, HO must go. So our conclusion, we reject H naught. We have sufficient evidence that the mean weight of peanut M&M bags is different from 49.3. Now let's talk about doing a confidence interval. We're going to construct a 95% confidence interval for the mean weight of peanut M&M bags. You might be tempted to go back to the t-test results that we just had, because you probably noticed that there's a confidence interval given to you right there on that output. And like I said, super tempting to use that. However, this confidence interval is different than the confidence interval that we want. This is not a confidence interval on the mean weight of peanut M&M bags. It's a confidence interval on the difference between your sample mean and the test value. So something totally different. So do not use this confidence interval. Okay? Instead, the correct way to do the confidence interval for the mean is going to be using the Explore option in SPSS. So in SPSS, you're going to go to the Analyze menu, down to Descriptive Statistics, and choose Explore. Once in there, you're going to take those M&M weights and put it over there on your dependent list. Then if you click on the Statistics button, it gives you some options here. So the default confidence level is going to be 95%, which for my example here, that's what I want to do. But again, this is another place where students sometimes trip up. On the exam, look very carefully at what % confidence interval they want you to do. If they want a 90% or a 99%, then you would need to come in here and change that percentage in order to get the correct answer. So in this case, I'm going to stick with that 95% because that's what I wanted from the problem. And once I click on OK, this is the results that I get. And you can see right there is my 95% confidence interval for the mean. I've got the upper bound and the lower bound. All right, so what can I say about that confidence interval? So here's a good way to give the conclusion. We're 95% confident that the mean weight for peanut M&M bags is between 51.490 and 53.049 grams. Now, there's a lot of wrong ways that you can write conclusions, and especially on the exams in this class, there's usually 1 or 2 questions that try to trick you up with ways, incorrect ways to give conclusions. So here in green, I have the conclusion that we just gave. This is the correct way to write a conclusion about this confidence interval. And now I'm going to show you some incorrect, some wrong ways you could write the conclusion. So here's a wrong way. You could say there is a 95% chance that the mean weight for peanut M&M bags is between 51.49 and 53.049. Okay, what makes this one wrong is this word chance. So once we've calculated our interval, we've collected the data, we've calculated the interval, there's no more probability associated with it anymore. We can't use words like chance or probability with a confidence interval that's already been computed. Okay, it's kind of like when you think about the weather. We can talk about tomorrow there being a 20% chance of rain tomorrow, but if you're talking about the weather yesterday, you don't say there was a 20% chance of rain, you know, that there is a 20% chance of rain for yesterday because either it rained yesterday or it didn't. Same thing here with our interval. So either our interval contains mu or it doesn't. There's no more probability because we've collected the data now. So don't pick anything that has the word chance or probability in it with your actual numbers, with the data that you've collected. Here's another one. We're 95% confident that the weights of peanut M&M bags are between 51.49 and 53.049. So the problem with this one is that our confidence interval tells us where we expect mu, the population mean, to be. It doesn't say anything about where we expect individual observations to be or future sample means or anything else. It just says, hey, this is where we're pretty sure that the actual value for our population is. So the thing that's wrong with this one is that this is saying, hey, the weights of peanut M&M bags, individuals. It's trying to say that individuals are going to have weights between these two values, which is incorrect. And one more wrong way to write a conclusion. 95% of sample means of peanut M&M weights will be between 51.49 and 53.049. So again, this one's incorrect because it's trying to say that future sample means will be in this interval. And that's not what our confidence interval says at all. Our confidence interval only says, hey, we're pretty sure that the actual population mean is between these numbers. So the only correct way that's on this page to write the conclusion is the green one at the top. All right, one other tricky little thing that sometimes students run across in this chapter is when they start asking you for margin of error, and the only thing that you have is a confidence interval. So to solve these kind of problems, recall that a confidence interval is just an estimate plus or minus a margin of error. So in this case, in this chapter, we're talking about x bar plus or minus a margin of error. That would mean that your upper bound is found just by taking x bar plus the margin of error, and the lower bound of the confidence interval is found by taking x bar minus the margin of error. And here's a nice picture of kind of what that looks like on a number line. So in this case, if we have SPSS and it's giving us the confidence interval, that means that we have the lower bound and we have the upper bound, and we can use those to find the margin of error. If you look here, between the lower bound and the upper bound, we have two margin of errors, two values of that margin of error. So if I were just to take the upper bound and I subtract the lower bound and then I divide that by 2, that's going to give me the value of my margin of error. So let's do that with the data that we have here. So here was my confidence interval. I'm just going to take the upper bound minus the lower bound divided by 2 to give me my margin of error. So my upper bound was 53.0487. I'm going to subtract the lower bound, which was 51.4897. I get that subtracted value, which ends up being 1.559. Divide that by 2, and ta-da! My margin of error is 0.7795. And you can go back and double check it just by taking your mean, which is also out in the output there, and adding and subtracting that margin of error and making sure that you get the confidence interval that you had. So I hope that you find this helpful for figuring out these kind of tricky problems there in Chapter 11. Have a great day.